New concepts, I suppose. We found the gradient function for any particular curve. Trying to answer a problem about things that change. See what rate they change at. So yeah, if you had a U-shaped curve or a quadratic curve like this, we were looking at how steep it is at certain points. Obviously, at this point, the curve isn't increasing that steeply, but at this point, the slope or the gradient would be higher. And we use tangents to show the steepness. And to get the tangent, we used two different points that were distance apart. This was called a secant, but we kind of wanted a bit more specific, so we made that distance as small as possible so we get it as accurate as possible. And that infinitesimally small distance is the whole theory of calculus. Getting that distance really small, so we could test at different points along the curve what the slope would be or the gradient would be. To do this, we did a thing called first principles, which used it's a new term, but the limits as something approaches zero. It as this distance, and I'll just let me redraw this briefly. As the distance between these 2 points gets smaller and smaller and smaller and smaller, in other words, we're trying to get it so it's at a point almost, but not quite at a point. We want that distance to be zero, but we can't actually say zero because that means that your rise over run, the run would be zero. So we want it so small that it's almost zero, and that's when we use limits. So we came up with this thing. As h approached zero, so h was that distance, h is the distance between these 2 points. As h approaches zero, if you put x plus h into the function, take away fx, that's actually the rise. So that's just, you've subbed in x into the function. Let's say this was x, you subbed it in, you get the y thing, and y would be just the function with x put in it, an x value. And then the next one up would be x plus h. And the difference between those two will give you the rise, so that's why you subtract them. And the run then was this distance of h. And what this thing says is we want that run to be as small as possible, infinitesimal, but still significant enough not to be zero. So it doesn't break the rules of dividing by zero. And this is what we came up with. This will tell me the grade. This is the gradient function at any particular point. This will create it. And this is something called first principles of calculus. Do a very quick example of that. So if we had a function, let's just say x squared. Simple function, that's very similar to that. If we had this function, we could find the slope at any particular point along it using this formula. So the function with x plus h put into it. So that's, instead of x, we put x plus h. And we need to square it. Take away the function with x put in it. Well, the function actually is just what it is. All divided by this infinitesimal distance h. If we multiply that out, worked it all out, we'll come to the limit. We'd apply the limit that almost zero in a second. That's going to be x squared plus 2hx plus h squared minus x squared all over h. So just squared out that bracket. And this x squared and this x squared disappear. And I'm going to divide in by h to simplify, because h can divide into both those terms. I get 2x plus h. And I divide in by h. This is all what we did yesterday. Now, I apply my limit now. I've simplified as far as I can. And as h goes to 0, this is pretty much 0. This h is pretty much 0, so you can ignore it. It isn't 0, but we can ignore it because it's pretty close to 0. It's so infinitesimal that distance is so small. So this thing we've created, this 2x, is the gradient function for this. And that means we can use this terminology, f dash x, and that gives me the gradient function. 2x. And that means I can tell the slope anywhere along this function by using this gradient function, how steep it is at any particular point, how it's changing. For instance, if I wanted to find the slope at -2 would just sub in here, 2 times -2, and I get -4. So the slope is downhill, quite steep at 4. The slope at -1 is 2 times -1, and that's -2, of course. So it's less steep, it's downhill still, but it's less steep. Slope at 0 then, gradient at 0 is going to be 2 times 0, that's 0 slope, so there's actually no slope there, so it must be flat. The slope at 1 is 2 times 1, and that gives 2. So now it starts to go uphill again. You see the way the slopes are matching what you imagine, they maybe not imagine, but they are matching what the graph does perfectly. The slope at 2 is 2 times 2, which is 4, so it's starting to increase the slope. It's getting steeper and steeper. And if you put in 3, you're going to get 6, so it's even steeper, and it's even progressively steeper. And that matches what the U-shaped graph is. At 0 on x squared, there is no slope. It's just at this point. It's no slope there. But when we start to go further up, the slope starts to increase. It starts to get steeper and steeper and steeper. And that's what this is showing. Now, there is a quicker way of getting from here to here without doing this. Laura wants us to get to as quickly as possible. She knows already cyclic first principles. And that's called differentiation by rule. That's what we're going to do today. But remember, the two important concepts of what calculus is, or what the first derivative is, f dash x, is, Bella, what is your understanding of what this is? When I do this, what have I done? So I've got this is the function, this is the original function. What is this representing? Good question, thank you.
I don't know.
You don't know, Georgina?
The slope?
Yeah, this gives me the slope at any point along the graph. Yes, it's all about, it's the gradient function or the slope. This is all about the slopes, the steepness of the curve at any particular point. It gives the slope at a point. Slope's other name is gradient. That's the gradient of the gradient of the tangent at a point, but it's just the gradient of the curve at that point, because it's constantly changing. That's the problem with curves. The slopes are constantly changing. Up till now, we're just dealing with ordered geometry when the slope was the same. This was a straight line. Okay, that's what we're trying to find out. We use this concept of a limit to find it, but there is a quicker way. That's what we're getting to now. When I find it. Okay. So now we're looking for patterns. And Laura can't talk. So we're going to look for patterns. I'm going to give you the function, and then I'm going to do the derivative straight away. And let's see if we copy it first. So there's one anyway. I'll get rid of all the rest of this. Okay, let's go. So here's a function. And here's its derivative. Here's the function. Here's its derivative. And function. Here is its derivative.
What's the derivative?
A gradient function. This is what the word we call it derivative. Anyone see any pattern?
The x's.
See it?
Find the.
You done this before? Yeah, Bella, see something? X
The
is
x is like, so that one's like 2x squared, that one's just x.
yeah.
And
This one's x to the 4 and this one's x to the 3.
I-
This one's x and this one's got no x.
Yeah.
Interesting, this one. That's a straight line. So that's 2x is just as a function. If you saw y is equal to 2x plus 3, it's a straight line, isn't it? Just 2x then would also be a straight line. And its slope function is just 2. There's no, you can't even put in a number. It's just a constant. It's constant slope of 2, which you know from coordinate geometry. This line has a constant slope of 2. And if I had 2x plus 3, the slope would still be just 2. There is no plus 3 at the end. You know that. They're all connected. Let's put up another one. See if your theories are being confirmed. This last one we'll do, and then we'll look. Should have done that right. All right. So Lucia, you were saying. What were you saying again? Also, like 4 times 3 gives us 12. That looks like something to work with, because this 2 times 2 gave this 4. This 2 times 3 gives us 6 here. Ignore that for a minute. Okay, yeah. And if there's no power, but it is the power of 1, 1 times 2 gives 2. That makes sense. 1 times 2 gives 2 as well. What happens if you see just a constant, these 3's? They just disappear, don't they? If this constant just disappears. It looks to me like the x power goes down 1 every time. And if there's no x power, like the constant just disappears. And as Lucia says, if there's a number in front, the x power multiplies by it. There's always a number in front, because if there's no x, there's no number, it's 1. So let's apply that. I'll just keep that on 1 for a minute. Let's see, can we figure it out? Let's write a cubic one. So let's just do x cubed plus 2x squared plus 3x minus 4. What would its derivative be by rule, looking at it? 3x squared, you're saying? Yes, because 3 multiplied by 1 would be 3, and then take 1 away. Yeah. What would be the next one? 4x, yeah, 2 times 2 gives 4. And take away 1 from the power, you're down to 1, so I won't write 1. And then plus just 3, yeah? This is just an x, and that's 1. Okay, so what about the 4? Okay, let's do another one. That's correct, yeah. Let's do another one. Let's do quadratic now. Let's do 2x squared minus 3x randomly. All right, so let's get the derivative of that. This is the first one done. Let's do another one. Let's see. Who will I ask? Matthew.
4x minus 3.
Yes. So 2 times 2 gives the 4. And 1 less power, so instead of x to the 2, it's x to the 1, or we just write x. And 1 times 3 gives 3, and x is gone now, because 1 take away 1 leaves no powers of x, and the 2 is gone. Wonderful. If I were to draw these, going back to what they actually mean, a cubic function, it creates a gradient function that is a quadratic. Does that make sense? Well, let's think about it. Cubic function. The slope here, is it positive or negative? Just here, it's, reading from left to right. What's the slope? Positive or negative? It's going uphill, yeah. Positive, 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 positive here. Yeah, it's probably 0. And then it's downhill, 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 downhill. 0 again, and then positive, 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 positive. Okay. How does that translate into a quadratic? These are positive numbers, yeah? As 2 times it gets 0. 2 places there's 0. And then there's a lot of negative answers. These are the answers to the slopes. This is the slopes. So let's think about a quadratic graph, what it would look like. 2 places it goes through 0 on the y-axis. Underneath here, all those answers are negative, aren't they? They're negative y values. And above this, these are all positive y values. Does that match what we have here? Yeah. Not a coincidence. So these are all the answers to the slopes of a cubic equation can be formed in a quadratic. All the answers give. And we did a little bit something similar to that when we were doing the discriminant. Remember, it had to be greater than, answers were greater than or less than 0. It was all about this. We looked at where the graph of the answers was above and below 0. It's something very similar. So the slopes can be represented on quadratic. And this one then, the quadratic, well, let's have a little look at quadratic over here. Quadratic in general has this shape. Which means starting here, that's negative, isn't it? Going downhill, 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 which is 0, and then continues uphill, uphill, uphill. Those slopes, do they form a linear graph? Kind of hard to represent, but if we just have any old linear graph, at some stage, it's definitely going to cross 0, but only once. And that makes sense here. This is only going to turn once. Quadratic's only going to change and flatten out at one point. There's no other places along it that we're going to get 0. That makes sense. And all the answers before that are negative. All these answers are negative. I'm not talking about the slope anymore. Just the answers are negative. And all the answers after it are positive. I'm referring to the y values, the answers, the outputs. And that matches that. And then when we have just I'll do one more down here. If you have just a linear, as we had 2x plus 4. It's just a linear one. Its slope, that's just going to be 2, as we discussed earlier. So there's a linear. Let's look at a line in general. If it's uphill, it's always uphill. It's always positive. And it's always the exact same answer. That's the slopes. Exact same answer. Never changes. It's constant. And that's why its gradient function is a constant number. Never changes. It will be 2. And that's it. Its slope is 2. Right. We'll return again and again to what the slopes mean at each individual point, but today we're going to concentrate on just getting from here to here. Now I've done this. How do I get from here to here? Also using by rule. Well, the 2x and the 2 hopefully make a bit of sense. This, not sure. Not sure about that one. How did I come up with that? It's just using your rules of indices. This is where all you've learned in numbers so far will be tested. Square roots, dividing by x squared. How can we convert that to a number where it's up on top of the fraction? What is it when it's converted? Using indices, laws of indices. 1 over x squared is the same as x to the power of -2. Okay, now apply the rules that we just did. Multiply down by the old power, so -2 multiplies down, still have an x. And what do I do to the -2? I subtract 1 from it, and -2 take away 1 gives -3. And then I apply, okay, multiply down by 1, I get 2, and then 1 take away 1, if you want to write that. That gives 0, which is just x to the power of 0, it's just 0. So that's where this came from. Manipulation. All right, you guys, I think it's time for you guys to do something. Just looking at by rule. So some here. Yeah.
Is there a rule or is it just that?
It's just that thing. This is a difficult way of writing it, which we can look at if you want. Or you just remember, you're never going to remember the way they've written it with x's and n's. They start to go x to the power of n, and then you do x to the n minus 1 multiplied by n. And you got this. Better off just remembering multiply down, but okay. See how you get on with these 4. I'll put them on the whiteboard in a second. First one, fairly straightforward. Second one, you have to apply some rules of indices. And the other 2, you also have to apply some rules of indices. The rules of indices are a bit suspect. I'll help you out with question 3. Square root of x is x to the power of a half, and that'll be 2 to the x minus 1. That's it. Powers we can deal with. So for 2, 3, and 4, you're going to have to rewrite it with the powers above the line, or no square roots as well as. Five, eight, x. Okay, I'm going to start to do them on the board for you. First one right at Julie. Nope. Lot of x. So 3 times 5 is 15, and then take away 1 from 3. It's 2. 2 times 6 is 12, take away 1. It's just x and 3x. Second one, I will first write with the powers, not fractions. And then I will get the derivative. Derivative of 7x is just 7. Minus 1 times minus 4 is plus 4. I'm sure someone wrote minus. And I need to take away 1 from 1. That's minus 2. Minus 3 times 3 is minus 9. Take away minus 4. Now, it's okay for now, but in general, it's good practice to put it back with no negative indices again. So that'd be 4 over x squared minus 9 over x to the power 4. Put it back below the line. This one I started for you. Half times 3. Ooh. 3 over 2. 1.5. X. Take away 1 from a half. That's going to be minus a half. Oh, it might be minus. Minus 1 times 2. Minus 2. Take away 1. Minus 2. That's my first derivative. I can tidy that up a little bit. X to the minus a half is going to be over x square root x. And 3 over 2, I can write like this if I fancy. Or any form of that is fine. And then it'd be minus 2 over x squared. So remember, x to the half is square root x. And x to the minus half is going to be 1 over square root x. And the last one. Firstly, I would write this with indices. Then I would apply my rules. 2 times 1 is 2. X minus a half times minus 4 is plus 2. X to the minus 3/2. So I subtracted 1 from a half. So minus a half, take away another 1, brings me to minus 3/2. How do I write that then? It's 2 over. How do I write minus 3/2? Laura? It is the square root of x cubed. All right. If you're getting this line, that's fine, and then you're not trying to remember your rules of indices, that's okay. So there's 4 answers to those. So these require practice. I'm going to put up a load of questions now. Some easy, some a bit more. All of them questions. I'll put these on managed banking in a second. Question 1, easy, like this style. And question 4 and 5 then require you to do some of this manipulation with indices. I would like you, because we have no class tomorrow, so homework. Any 20. They're quite quick. So, but any 20. So if you run a simple 20, so there's 20 parts. Oh, it's 4 times 5. The question 1 alone has 20 questions. So if you just want to do question 1 and that's it, that's fine. But perhaps push yourself a little bit harder than that and do some from question 4 and 5 after you do some from question 1. Okay. Get going. Any 20 questions from that?